Good morning and welcome. Today we are going to talk about CUDA capable devices or GPUs and how to program them. So let me share my screen and let's get started. So hopefully you've enjoyed your readings and got a little bit of information about how they work. We're seeing that CUDA capable devices give us much speed up in our calculations, and this can be very useful for scientific computing. One of the great things is that gamers and computer scientists have been collaborating together to push the development of better hardware for us to use, not only to enjoy for better games, but also to do better scientific computing, which is the key thing that we are interested in this class. So let me just bring up these slides and let me get you into the correct display setting. And we can go ahead and get started. There we go. And ta-da! All right, great. So, introduction to CUDA and GPU. So what exactly is CUDA and what is a GPU? So this here is an image of NVIDIA's Titan X. This is top of the line processor that's available, a top of the line GPU graphics card. And we'll be learning about this today. CUDA stands for the Compute Unified Device Architecture. And it is the NVIDIA platform on which other languages are built to talk to the GPU hardware. In a sense, it's almost like a little standalone and very powerful computer in and of itself, as we will see as we explore more about the hardware in GPUs. So GPU computing, as I was mentioning, has evolved out of the gaming community. GPUs were initially developed to increase the speed in graphics processing, which has high demand when people are playing games. And of course, the graphics need to update in real time. And so some of the things that people wanted to do with the graphics is to have more realistic graphics, to have better shading and so forth. So there was this need for that to happen. CUDA was developed for graphics shading, as I just mentioned. Basically how it works is to add features from an existing language, mostly C. DirectX and OpenGPL compute shaders resulted. So the way in which the three-dimensionality of the graphics is rendered is by shading of the colors. So you start with a basic outline of, say, a figure, and then to make it look more 3D, to get the more sophisticated and realistic looking graphics. That's achieved by layering on top of that a kind of a shading to make it look more real. And so what needed to be done is that needed to happen more quickly so that it would update and it didn't slow down the game. However, in time, others realized that this could be an incredibly useful application as well. So this is a general purpose computing on GPU or GPGPU. There was a need for writing apps in domains other than graphics that use the GPU hardware, like us, who might want to do some computations. This drove GPUs to evolve from a niche, that is from the graphics, to a more general audience. Maybe you enjoy programming too, so that's great. We can use GPUs for many things. This is the example of what kind of a GPU we have on our machines. So these are available on the N78 and the EXX96 nodes on the cluster. Also, the two machines that I have in my research lab, our desktop servers, also are running the GeForce GTX 1080 Ti. This still is a really very high performing GPU. As you can see, it's NVIDIA's flagship GPU marketed towards the gamers. However, this GPU, although it came out in 2017, is still pretty much at the top of the market. The only one which is outperforming this is the Titan, and the Titan comes with a commensurately larger price tag with not so much of an enhanced speed up and so forth for what we would be using it for. So this is really a very excellent choice for a reasonably well priced and high performing graphics card to use for scientific computing these days. The GeForce GTX 1080 Ti runs on the Pascal GPU architecture. It also has 11 gigabytes per second as its memory speed, according to NVIDIA, their manufacturer. So I thought it might be useful to go through some of the specifications and what actually they mean, just in case you don't know exactly what those meanings are. So we will talk through those. There are some things that are used somewhat colloquially that are not exactly correct. So we will be just clearing those up and making sure we have an excellent understanding of what the definitions mean. So what do the graphics card specifications mean is what we will be delving into. So a graphics card or a video card, in fact, is referring to that whole box. So what we were looking at right here, this whole thing is the graphics card. And as you might notice right over here on the side, we have these contacts sticking out, these metal contacts like you would have on many kinds of cards. That's what actually plugs into your motherboard and how that actually interfaces the rest of your computer. So when we say a graphics card, we in fact mean that whole box. And because of the use of it for video games, this is sometimes called a video card. So a graphics processing unit, or the GPU, is in fact actually only the chip that does the processing. It's only one of the many components that actually sits inside that box. There can be more than one GPU in the same card because there could be more than one GPU sitting inside that box. It's a possibility. A graphics card may have some differences, such as a number of cooling fans and other peripheral hardware, but they are based on a specific chip, as we'll see in the NVIDIA series that I will show you next, or the actual graphics processing unit. There can be more than one GPU in the same graphics card. So this is an example of the NVIDIA models that all have the same chip. However, the things that are different are, of course, as manufacturers make these things and they put them into these boxes, they may perhaps, include better fans, or they may have more ports for data processing and so forth. And those could be some of the ways that these boxes could be different, right? So here we see the GTX series out of NVIDIA. We see some of the earlier ones. This is our model sitting right here. And we also have the GTX 1070. The major makers of GPUs are NVIDIA and AMD. So NVIDIA is the one that we are going to talk about today, just because they are dominant in the resources that we're going to be using here at Wesleyan. So as mentioned, we have the models we've just looked at, and those are both on the cluster and on the workstations that we have in my research lab. And for the exercises we're going to be doing this week, we may be actually using some of each, or possibly logging onto my research machines to have better control of what the GPUs are doing as you are learning how to do the GPU programming. The next thing we're going to talk about is the video memory, which can be called a video RAM or VRAM for short. This is random access memory. So what it's important to understand is that the video card, in fact, has its own memory. So just as a CPU has associated memory, as you might know from some of your computer classes, that's necessary in order for the CPU to run. So how does it actually work? So in short, for example, if you had some data on, say, a key like this, right? You cannot actually calculate off of the key, right? You need to actually transfer the data that's needed by the CPU in order to do the actual execution of the program into the RAM in the computer. And so similarly, video memory video cards need to have their own memory that their GPU is actually accessing. So it is not accessing the same memory that is being used by your CPU on your machine. It has its own. So it's kind of like a mini computer in that sense, in that it has some resources kind of like duplicated, if that makes sense. So what this means then is that the chipset will actually have its own associated video RAM. And so because it's separated, it's going to hold the data that is going to be processed by the GPU, and of course not the data that's being processed by the CPU. So generally speaking, the more RAM we have, the faster the GPU can process, because it's not waiting for information transfer to its video RAM. So typically we say, as a rule of thumb, these days you want about 4 gigs. 2 gigs is on the lower end, and 6 to 8 gigs is what you might get for a higher end machine. However, that is not the only consideration, and we have this little analogy here with some roads. You can have all the memory in the world, but if you can't get information in and out, what good is it? So maybe we think about a parking garage, and you want to have a great business at your parking garage. So this is analogous to having data resident on the VRAM. And so if you have a highway that's going back and forth, lots of vehicles can get in and can get out very easy. There's multiple lanes here, so we have great bandwidth. However, in contrast, if we had this country road leading up to it, you know, you'll be lucky if you get 2 cars passing on this without somebody driving off the side of the road. And so we see that the bandwidth is considerably lower. So when we're talking about memory bandwidth, this is going to be measured in gigabytes per second, and we're asking how much data can be moved in and out of the VRAM per second. So overall performance will depend on how much VRAM you have and how quickly the data can be moved in and out of it. This brings us to the core clock. So the frequency at which the GPU is running is going to be told by the value of the core clock, and that will be reported in hertz or a variant of it. So frequency means how many calculations per second, right? Because hertz generally means 1 event per second, and the event we're talking about is a single calculation. The event here is going to be that calculation, and computers can, of course, do many more than 1 calculation per second. So you may, for example, see the speeds in some variant of hertz, like gigahertz, in terms of the core clock speed. But the core clock speed also has some trade-offs. So the processors, interestingly enough, are sometimes capable of working faster than their actual clock speed. But the problem is when the GPUs are running and they're doing calculations, they're in fact giving off heat. And so when they're under heavy load and they're trying to do many calculations one after the other, the issue is that the machine is going to heat up. Now, notice that computers have plastic in them, right? Okay, so we talk about computer meltdowns, and we mean this in the literal sense, that when it becomes too hot, the plastics can actually melt. We also have other things that are temperature sensitive. There's the soldering and so forth. So we cannot get our computers to heat up too much. GPUs can safely run to about 91 degrees Celsius, which is about 195 degrees Fahrenheit. To give you an idea, that is a little bit below the boiling temperature of water, so pretty warm. If you touch my machines when they are operating at their peak performance, yeah, it's warm. You may retract your hand from that because it feels a little hot. So you don't want your machine to be running too hot. And so that is why having a cooling system is needed to keep the temperature down. And so, of course, the machines are monitoring, right, and running slower if the temperature gets too hot. So there is that trade-off in terms of how the machines run. Interestingly, if we get the opportunity to go up to see our actual cluster in the science tower, one of the striking things you will notice as we walk into that room is the sound of the air conditioners running. Well, why are we running air conditioners year round? You know, it's cold out. The reason is because the machines are producing that heat, and we need to dissipate that heat by cooling them down. So we have the air conditioning system to help with that. And of course, the fans on the machines themselves are helping to circulate the air to reduce the heat on them so that we do not have any meltdowns. So that brings us to actually getting started with the CUDA programming. So we've started to see some of this in your readings, and I thought that I would give you some additional background information and take you through some of the basics in preparation for our activities we'll be doing later in the week. So the design goals behind CUDA programming was scale to many cores and create many threads, which is what will help the program to run faster. We want programmers to focus on parallel algorithms, not on the mechanics of a parallel programming language. And so this will enable heterogeneous system use. It works best on GPUs, but it is also possible to program on the CPUs. I would mention that the GPU programming, the CUDA programming, is perhaps not really a standalone computer program as we typically think about, say, Java or C or Fortran or Python, because it's not really the sort of a programming language you would just use on any architecture. It really is specialized for working with the GPUs. And so the reason why it's like this is because we want to think about where do we need to have that additional information. So the idea is that we're going to hopefully be programming in a reasonably familiar programming language, C, and then there are going to be additional libraries and so on in the C language that are going to interface with that hardware. So what the CUDA is really doing is it's really extending the current programming languages to allow them then to interface with the hardware. And that is basically what it is meant to do, not necessarily to be a completely new programming language in and of itself per se. The CUDA kernels and threads. Let us understand a few definitions. So the device, when we're referring to that, is the GPU, and the host was going to be the CPU, the central processing unit, which we have been using in computers since forever. The kernel we should think of as being a function that runs on the device or the GPU. So then we have the parallel portions of an application are executed on the device, the GPU, as kernels, which is the function running on that particular device. One kernel is executed at a time on one device. A CUDA kernel is going to be executed by an array of threads. So all the threads are going to run the identical code, and that is what is being depicted here. So we have some identical code being represented by this box, and we see that we have a series of threads here. Now what is going to be happening is that the thread IDs are going to be able to operate independently. Each thread has an ID that it uses to compute the memory addresses and to make the controlled decisions independently of the other threads. Note also that this is a form of parallelization in and of itself, because setting up an explicit loop is not required. The looping becomes implicit when the threads are generated by the kernel. There are some functions that are useful to know. The kernel designated by a function qualifier is this global. We notice that these are offset by the double underscore around the global. This function is called from a host and executed on a device, and it must return void. Other CUDA function qualifiers are the device and the host. So we see that the function is called from the host. So recall that the host is the CPU and executed on the host by default, or it can be sent out to the device or the GPU in order to carry out your calculation. Notice that the device cannot be called from the host code, which makes sense, and vice versa. We are not going to have the host being called by the device code. This brings us to some information about launching the kernel. So here we have the modified C call syntax. So here we have kernel, and then we have this triple chevron notation here where we're going to specify dimension 3 dg and dimension 3 dB. So what does all this mean? So here is our chevron notation. So this is what is going to offset this. And here we have the dg. This is the dimension and size of the grid in blocks. So for 2-dimension, we have x and y. The blocks are launched in the grid as dg.x by dg.y. dB is the dimension and size of the blocks in the threads. We have the 3-dimensional example, x, y, and z. So threads per block, we would have db.x by db.y by db.z. Unspecified dimension 3 fields are going to initialize to 1. So there are some built-in variables. All the underscore global and underscore device functions have access to these automatically defined variables. This is going to improve the speed and also reduces the amount of code that is actually need to be written by the programmer. So dimension 3 grid dimension, this is the dimensions of the grid and blocks. This is the dimensions of the blocks in the thread, dimension 3 block dimension, right? So we've seen these, the block index, this is the index within the grid, and we also have the thread index within the block. So these are actually the variables, the built-in variables that are going to actually manifest that, that parallelization, that automation that is happening all by itself. So built-in variables are used to determine the unique thread IDs. We can map from the local thread ID to the global ID, which can be used as an array index. So here we can see that the local thread IDs are going to be indexed from 0 to 4 because there are 5 threads in here. However, we can take into account the block index and we can use that into a formula that will allow us to work out unique identifiers so that we see that every thread has a unique index, but locally they can have the same index as they may have in a different block. It's important to take into account the host synchronization on several levels. When we're talking about this, what we're mentioning is this idea that we may have some calculations that are being carried on. And it would be important to get the answer from other calculations that are happening simultaneously in another location before we can proceed to the next step. So say, for example, there are some calculations that need to compute some totals and we need to get a grand total. So suppose that after 3 have completed their calculation, they wanted to move on. Right? The problem would be that we wouldn't be able to get the grand total until the remaining 2 actually finish. So we need to take into account this synchronization to ensure that we have all of the information that is required in order to carry on to the next step. The implication of this is also that we are beholden to the slowest calculation in order to proceed any of these potential bottlenecks. So all kernel launches are going to occur asynchronously. This control will return to the CPU immediately. The kernel executes after all previous CUDA calls have completed. So this means that we may have, for example, more than one kernel in the same program. And so we need to run that kernel and then we need to complete it. And then we need to move on to the next one. The CUDA memory copy is synchronous. So the control returns to the CPU after the copy completes. Copy starts after all previous CUDA calls have been completed. And the CUDA thread synchronize is these blocks are going to be active until all previous CUDA calls are complete. So there are some built-in vector types. These can be used with both GPU and CPU code. Notice that these are another way which data can be parallelized. So this is showing you what the syntax would look like. The structures associated with X, Y, and Z and W fields, we're going to have the unit for parameter and init y equals param.y. So we see that this is how we might access a particular instance inside of this, right? This is indexing that is similar to indexing that you may have seen, for example, in Python arrays. Dimension 3, this is based on unit 3. This is used to specify the dimensions, and by default, the value is going to be 111 for 3 dimensions. dimensions. So this illustrates how CUDA code is going to be compiled. So first we have the C or C++ CUDA application. So again, this calls to mind the idea that CUDA is not completely freestanding, but is based on the C programming language. So we'll have some C code that is CUDA enabled, perhaps involving some of the things that we have been looking at just now. We're going to use the NVCC in order to do the compiling. And so then we get out CPU code over here, while the rest of it moves on to the PTX. The PTX will then go to the target compiler for whichever particular machine is being used in this application. This shows you some examples of the syntax of using the NVCC compiler. So for example, we do NVCC filename.cu for CUDA enabled and -o for an executable if that is what you will be getting. So that would be the typical case. This will build the release mode, or this would be your final product. You can also run it in the debug mode, and this will give you some additional output that may help you figure out what could possibly be issues with your code. It can debug host code, but not device code. So we're going to talk about the incrementation of arrays, and this will be illustrated by the differences between a CPU program and a CUDA program. This is essentially the heart of what we'll be having a look at later on in the week. So if we start off with the CPU-based program here, we see that we're going to have a loop, right? So this is going to be doing looping, and we notice that we have explicit indexing here where we are incrementing this loop by 1 each time. And we notice that that is replaced by this over here, which is having the looping occur automatically, and that we do not any longer need to have the individual indexing. It is happening by itself. Then we notice that we also here on the left have a function call. And here on the right, we also have a function call, but also we have needed to set up our dimension 3s for the dimension blocks and the dimension grid over here in order to carry out the calculation. So we'll be learning step by step how to convert a distance-based program from a CPU program over to a CUDA program. So that brings us to actually programming the GPUs. That's a perfect segue into what we're going to be doing. So we're going to be working with a sample C++ program. We will compute the distance from a reference point to each of n equally spaced points on the interval from 0 to 1. The input is going to be n, the number of points. This will compute the coordinates for equally spacing the endpoints from 0 to 1. It will calculate the distance from each of the endpoints to the reference point. In version 1, this uses a for loop to call the function that evaluates the distance for a single input value. The simplest version of the program that is a candidate for parallelization is illustrated by this code. In version 2, we ask about what improvements we might be able to make. So this illustrates the data being sorted into an array. The loop is moved into a function named distance array. This is more efficient because it is able to manage the data as an array rather than excuse me, rather than a series of single data points. The function distance array is called once, excuse me, it's called once to automatically loop over and store all of the output distance values rather than having to be called multiple times. But is that the best we can do, or could we do even more? So in the distance parallel version, we will be talking about how we can take the principles from the readings in chapter 2 to create a parallel version of the code that takes advantage of the GPUs. This will compute the identical thing. However, we are expecting that it will run faster, and we will be checking out to see whether or not that's really true. All right, with that then, I just wanted to mention the fact that we have only covered the basic features, and there's of course much more to learn about CUDA programming. I highly recommend the NVIDIA website, which has many of the resources that we've been discussing today. As a matter of fact, as you might have gathered from my footnotes, we in fact actually have been looking at a lot of the information from the NVIDIA website already today. So I would encourage you to take a look at that. And there's much more to learn. And of course, your book also is an excellent resource, which I'm happy to share with you if you have any additional questions or wish to delve into more information about that. Alrighty, then with that, we are ready to proceed on to the discussion, and we will see you next time for actually doing our lab exercise, which will involve writing your first parallelized program using GPUs and CUDA programming. See you next time. Thank you very much. Bye-bye.